Good day. I'm Norman Wahlberger. Definitions are very important in mathematics and especially important in geometry, where our natural intuition often tempts us to forego proper definitions. Today we're going to talk about a subject which often isn't pinned down very precisely in elementary courses: how to define quadrilaterals, quadrangles, and more generally n-gons. So let me remind you that we're talking just about basic elementary geometry, everything built up over the rational numbers, and we have been talking about points. So a point for us is just an ordered pair of numbers, say x, y. And we've been talking about lines. For us, a line is a triple A to B to C of proportion enclosed in pointy brackets. And we have a relation of incidence between points and lines in terms of this equation here. And we talked last time about the definition of a triangle. This is just one of several possible definitions, but it's a very convenient one. For us, a set of three non-collinear points is what a triangle actually is. So here's points A, B, and C. They are not collinear. In other words, they do not all lie on a straight line. And so they define a triangle. And precisely it means that the triangle is actually a set. So it's a set containing three objects. The three objects are these 3 points. So if you want to look at it more carefully, each one of these points would actually be an ordered pair enclosed in square brackets just like that. And I remind you that the set notation means that the order in which we write these 3 points doesn't matter. So this set is also the same as the set BCA or BAC. And here's our notation for the triangle ABC, just the 3 points with a bar over it to denote the triangle. And I just make sure that we understand that if you have 3 collinear points, like these points D, E, and F, then this set is not a triangle. It does contain 3 points, it is in a set, but the 3 points are collinear, so technically it's not a triangle. Alright, so with those foundations, now let's ask, how do we define a quadrilateral? The analogous object with 4 points instead of 3. When it comes to quadrilaterals, it's tempting to just use a picture, to write down something like this and say, well, there's a quadrilateral ABCD. But we want a more precise definition, and here's one way of proceeding. So let's have a good look at this definition of a quadrilateral. We say that ABCD with a bar over it is a quadrilateral, means it is a list, A, B, C, D, of distinct points. So there are 4 points in a list, no 3 of which are collinear, with the further convention that A, B, C, D, that quadrilateral formed from 4 points in that order, is the same as the quadrilateral B, C, D, A. And also that ABCD is the same as ADCB. So let's have a look at what the definition means. First of all, we have 4 points. And we have a list. This is different from a set. In a list, the order matters. There's a first element, a second element, a third element, a fourth element in this case. So in a list, we are not allowed to change things around like that. Okay, and we're insisting that no 3 of these points are collinear. That's clear enough. And what's the significance of these 2 conventions? The convention is here that we are allowed to rotate our list. So if one person says, oh, this is A, B, C, D, another person could come along and say, no, this is the quadrilateral B, C, D, A. And it would mean exactly the same quadrilateral. So in other words, which of the points we're starting with in our listing of them doesn't matter. The cyclical order does. And this rule captures that property. We're allowed to rotate the A from the beginning to the end. And of course you're allowed to do it again, so you could rotate that B around to the other side. So the same quadrilateral would be CDAB. Now what's the meaning of this convention? It means that you're allowed to go in the opposite order and you have the same quadrilateral. So not only are we allowed to start anywhere we want to, but we're also allowed to go in either direction, this way or this way, when we're listing those 4 points. This makes it very clear what exactly a quadrilateral is. And let's note that ABCD, that quadrilateral, is not equal to ABDC. So ABCD, that's one quadrilateral. ABDC, in that order, that is a different quadrilateral. Okay, and here are some additional conventions about the quadrilateral ABCD that we're talking about here. We say that the points of the quadrilateral are exactly these four, A, B, C, D. Those are the points of the quadrilateral. We say that the lines of the quadrilateral are these four lines, AB, BC, CD, and DA. The other two possible lines that you could create, these ones here, we call them diagonal lines. So they're separate from lines. They have a different relationship to the quadrilateral. In projective geometry, which is something we haven't introduced yet, there is a complete symmetry between points and lines. That's not the case of Euclidean geometry, but in projective geometry it becomes very interesting to talk also about quadrangles, which is basically exactly the same kind of definition, but we replace points and lines with points throughout. But for elementary geometry, the notion of a quadrangle is really superfluous. It's really not needed. The quadrilateral suffices for most purposes. Let's have a look at how we generalize the notion of quadrilateral to an n-gon, like a pentagon or a hexagon. So what is an n-gon? We choose an n, a natural number, bigger than or equal to 3 to start with. And then we say that an n-gon, labeled A1, A2, up to AN, with a bar over it, is by definition a list. It's a list, A1, A2, up to AN, of distinct points with some conventions. First of all, you're allowed to rotate the first point to the end, and you have the same n-gon. And you're allowed to go through those endpoints in the opposite order. Instead of A1, A2, up to AN, you're allowed to say AN, AN minus 1, through to A1. So those two ways of ordering are the same. And finally, we agree that no three consecutive points are collinear. So for example, here's a 5-gon, A1, A2, A3, A4, A5. It happens to be non-convex, but that's all right. So that n-gon would be the same as the n-gon A2, A3, A4, A5, A1. Or A2, A1, A5, A4, A3. And the condition is that no three consecutive points are collinear. So A1, A2, A3, they're consecutive. Or A4, A5, A1, they're also consecutive. And no three consecutive points are collinear. Here's a 6-gon, which is also non-convex. A1, A2, A3, A4, A5, A6. Now we have some collinear points, or almost collinear. Those 3 points might be collinear, but they're not consecutive, so it still counts as an n-gon. Here's another 6-gon, 1, 2, 3, 4, 5, 6 points. This one here happens to be convex. Of course, the theory of n-gons in general is rather complicated. Even quadrilaterals form a rather rich subject for investigation. But I wanted today just to clarify the idea that it's important in mathematics to be fussy about definitions and to make sure that even things which appear familiar need proper definitions and precise definitions. Next time we are going to move on to our third major branch of mathematics. So far we've been talking about arithmetic and geometry. Next is algebra, the third most important branch of mathematics, which forms a bridge between arithmetic and geometry. And of course is a bit of a problem for many students. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.